These are the 2.2 Part 2 video notes. And we're going to continue looking at density curves and normal distributions. So the first thing that we're going to look at is the standard normal distribution. The idea of the standard normal distribution is to take a normal distribution and then standardize it. So go through and figure out what your z-scores are of all your data points. If you recall from our activity when we were looking at the test scores of the class, we went through and transformed that and turned them all into z-scores. When we turned everything into z-scores, we saw that the shape and the general description of the graph was the same. We changed our mean, we changed our standard deviation, we changed the spread, we changed where it was on the number line, but what we did not change was the shape of the graph. That graph still had the exact same principles regardless of what we subtracted or divided from it. So the shape stays the exact same. Now, why would I want to take a distribution I already know is normal and then find a bunch of z-scores? Why do I want to go through all that work? Well, what you're going to see in our examples is that by finding z-scores, you're able to figure out percentiles a lot easier. Finding a percentile without a z-score, you're going to have to compare where your number is compared to where it falls next to everything that came before it. You have to get all your data in order. And sure, you might say to yourself, okay, I can do this with data of 30 and 40. But when you get out into the real world, if you're a college board worker and you're trying to send out what is the percentile score for this ACT taker, you're going to be getting in millions upon millions of data points for the ACT. And to figure out what is the percentile of that person taking the ACT, it's going to be so much easier to use a z-score and basing it off the mean and standard deviation of all the test takers, as opposed to getting a full length of the data, putting it all in order, and then putting it proportionally where it goes. Z-scores will tell us proportionally where it goes based on that data. So a standard normal distribution still looks like anything you've ever seen. Your mean is at 0. It's at the center of your distribution curve at the peak. Between your first standard deviations, you have 68% of the data. Between your second standard deviations, you have 95% of your data. And between 3 standard deviations, you've got 99.7% of your data. Now, here's the good thing about standardizing your information. We can look here and we can see that this is table A in your book. And your book doesn't really do a great job of describing where table A is. It's in the back. So if you look, if you go all the way to the very back in Appendix B, it has A18, it talks about the TI Inspire. And then you go back a couple pages, you'll find table A in your book, and it kind of describes what's going on. I've got a picture of the positive side of table A. I did not also include the negative side of table A. This allows me to go through and use any z-score to find the proportion. And I think that this is going to be easiest to explain if I go right into examples. So, let's look at the examples here. Use table A in the back of your book to find the proportion of observations from a standard normal distribution that fall in each of the following regions, and in each case, sketch a standard normal curve and shade the area representing the region. All right, so for number 1, I'm looking for the z-values that are less than 1.39. And I have to be able to read what it's asking me. This is saying, what is the proportion of z's that are less than that value? So I'm actually just going to have to find what this value is. So I figure out if I've got a z-score of 1.39, what's its proportion? 1.39, I go up to the z-score of 1.3, and then I look at the tail end of it for 0.09. This means that my z-score is this value right here, 0.9177, and this represents my proportion as well. I'm talking about the z-scores that are less than this. So here's where 0.9177 falls my proportion. I honestly don't know if that's where it falls. That's just a generally good place where it would fall. And I'm saying these are all the z-scores that are less than it. So this is the proportion of z-scores which fall less than this value. 0.9177% of z-scores fall less than that value. Number 2 is a little bit more complicated because I'm looking for the z-scores that are going to be greater than negative 2.15. Again, I don't have the negative table A in these notes, but they're in your book. And I will show you where they are in class. Negative 2.1 5, you go to your table A value, and you find that negative 2.15 proportion is equal to 0.0158. Now, I'm going to go ahead and place this on the normal curve. That's going to fall like way over here, really, really close to the left side. I'm looking for the z-scores that are above that, though. I'm not looking for the z-scores that fall below that. So I'm looking for everything to the right of this value. That means I've got to do 1 minus 0.0158, and you'll just plug that really quickly into your handy-dandy calculator. So 1 minus 0.0158, and I end up with a proportion of 0.9842. And this is my answer. This is the proportion of z-scores which lie above that value. The alpha table only tells you how many z-scores lie below it. It never tells you how many z-scores lie above it. You can just subtract it from 1, though, to figure that out. The last one we have is number 3, and that one is asking us to figure out what is the proportion of z-scores that exists between two z-scores. So what I will do there is I will figure out, A, what is my proportion for negative 0.56. I go to negative 0.5, I find negative 0.56, and that proportion is 0.2877. What is your proportion for a z-score of 1.81? So this I can show you again because I've got the positive alpha. I go to 1.8. I go to the 0.01, so I get 1.81, and I find that this has a proportion of 0.9649. To figure out what lies between these two, I'm going to do my greater proportion minus my lower proportion. And with this, I can say that I've got 0.6772, or 0.6772 of the data falls between. I'll put like 0.287 here, 96.49 here, and then this is kind of what exists between them. So that's the representative of those between them. So there you go. That's how I would go and figure out what is the proportion of data points that exists based on these z-scores. I use my alpha table and go there. Now we can work backwards as well. And I'll do number 4 and number 5. I can figure out what is the z-score that relates to a specific percentile. So this first one is talking about the 20th percentile. This is going to fall in my negative alpha table, unfortunately, but what I do is I just start looking through my proportions, and I'm looking for the proportion that's closest to 0.2. And I'm going to find a proportion of 0.2 somewhere in this textbook, and I get a really, really close one. And I see that I've got a proportion of 0.2005. That is essentially the 20th percentile. It's the 20th 0.05 percentile. I'm calling that the 20th percentile. This z-score is negative 0.84. So your 20th percentile falls at negative 0.84 for a z-score. I work backwards. 45% of all observations are greater than z. If 45% of all observations are greater than z, that means I'm looking at the 55th percentile. Because if 45 are greater than z, that means 55 are less than z. So I go up to my table and I start searching for the 55th percentile. This one I'm going to do a little bit of an estimation because I can see here I've got 0.5478. Over here I've got 0.5517. So the 55th percentile is actually going to fall in between these two values. And I'm just going to call it 0.5. So this occurs at a z-score of 0.125. Again, I'm doing this estimation because I can see that the 55th percentile falls between these two. So I say z is equal to 0.125. Might not be perfect. I'm going to have to do a few of those just kind of estimations in between. I can see that neither one of these is particularly close to the 55th percentile. This one is 22 away, that one's 17 away. Theoretically speaking, 0.13 would be closer to the 55th percentile, but I'm still going to split the hairs here. So that's how we use our alpha table. Now, we don't want to just use our alpha table with z-scores. We actually want to start applying it a little bit. So I've got a check for understanding that's from the book, and it's using some word problems from the book. So number 1 and 2 apply to this cholesterol of teenage boys. The second one applies to driving lengths of Tiger Woods practice drives. So let's just kind of dig in here. We want to figure out the cholesterol levels above 240 milligrams per deciliter may require medical attention. What percent of 14-year-old boys have more than 240 milligrams per deciliter of cholesterol? So here we can see that the mean is 170 milligrams and the standard deviation is 30. So for number 1, I'm going to do 240 minus 170 over that standard deviation of 30. That's going to give me 70 over 30. And 70 over 30 will give me a z-score of 2.33. So I'll go up to my table A. I'll go to 2.3. I will go to 0.33, which is going to be here. So that means 2.33, a z-score of 2.33 falls at the 99.01 percentile. This means that 99.01% of 14-year-old boys have cholesterol less than this. But that means that what percent of 14-year-old boys have more than this? Well, that's the 100 minus that. So we do 100 minus this percentile because 99.01 have less. And this is equal to 0.99%. So 0.99% of 14-year-old boys have cholesterol issues that they should see a doctor about, according to this. Our second one, people with cholesterol levels between 200 and 240 are at considerable risk for heart disease. What percent of 14-year-old boys have a blood cholesterol between these? Well, I've already found my proportion for 240. My proportion for 240 is 0.99. I do need my proportion for 200 though. So 200 is 200 minus 170 over 30 is equal to 30 over 30, which is 1 for my z-score. When I have a 1 for my z-score, we already know that this falls at the 68th percentile, but we can still look at our standard table. Well, not the 68th percentile, it's 34 plus 50. And then your table will even tell you that this is actually even more specific than that. 1.00 is at 0.8413. And we can look up here at our z table. We've got 1 as our z-score and 1.00 is at 0.8413. And this makes sense because, again, if 68% of data falls between the first two standard deviations, one standard deviation above the mean means that we are looking at half the data plus half of that 68, so that's 84% of your data. Now to figure out what percent of these 14-year-old boys have to be concerned about their cholesterol, we'll do 0.9901 minus 0.8413. So 0.9901 minus 0.8413 is 0.1488. So that means 14.88% of 14-year-old boys are at risk. All right, last question. What distance would a ball have to travel to be at the 80th percentile of Tiger Woods' drive lengths? So first we got to figure out what is the 80th percentile of Tiger Woods' drive lengths. Oh, well, first we got to figure out the z-score that correlates with the 80th percent. So I look for where the 80th percent is. I'm going to say that 0.7995 is the closest to the 80th percent. So we're going to call that 0.84. So 80th percentile here z-score of 0.84 is equal to your 80th percentile. So then I go through and I see up here with Tiger Woods that he has a mean of 304 and a standard deviation of 8 yards. So to get a z-score of 0.84, he has some drive length minus that mean of 304 yards divided by his standard deviation of 8 yards. And now I go through and I solve for x, just like any algebraic equation you've ever had. So you do 0.84 times 8, and then you're going to add 304 to it, and you will find that the 80th percentile of a drive length for Tiger Woods is 310.72 yards. So here, the only difference once you have actual real-life data is that you're going to use the z-score at some point. And you're going to have to use the mean and the standard deviation that's given to you, or you're going to have to find the mean and standard deviation in order to get your z-scores to work with the percentiles and the standard normal deviation. All right, we got to check for normality though. So we can't just say, we can't use these tables. We can't use our A table with a non-normal distribution. If your distribution isn't normal, then these percentiles don't line up. It's not good enough. We have other ways of figuring out percentiles for non-normal distributions. We like normal distributions because figuring out the percentile is way easier with the z-score. But again, it only works for normal distributions. So, to determine your normality, the first thing that you need to do is make a histogram or a dot plot of the distribution. If it is roughly symmetrical, unimodal with a peak in the middle, it may be normal. If you see something that is very clearly left skewed or very clearly right skewed, you can go ahead and say that it's not normal. Again, if you look at the salaries of the Los Angeles Lakers, you know that it's not normal. It is extremely right skewed. It's something that those are only in the cases where it's very clear. If it looks like it might only be slightly right skewed, move ahead and keep checking for normality. Find the standard deviation, and then you want to find the mean plus or minus 1 standard deviation, plus or minus 2 standard deviations, plus or minus 3 standard deviations, and figure out the percentage that it would correspond to in your data. So see how close that would fall to the 68, 95, 99.7 rule. And if you end up kind of with that 68, 95, 99.7 rule, then you might have something that is normal. And then finally, this is probably the truest test. Plot your data versus the expected z-score based on its percentile. So you look at your data, you figure out what the percentile of that data is, you find its actual percentile, and then you plug that data point in based off what the expected z-score should be in a normal distribution if that is the percentile for that data point. We're not going to do this by hand. Never do this by hand. Always use a graphing utility for this. I will show you how to do this on your TI-83 calculator in class. But you want to have the idea of what we're doing is you are figuring out the actual percentile it is. And then you are using that actual percentile to say, okay, if this were a normal distribution, what should its z-score be? And then you plot the expected z-score of that percentile versus your data point. If you end up having a straight line or something that looks like a straight line, you have a normal, you have something that could be normal. And that's probably the truest test for normality is that. So I've got a determining normality example here. This is from our activity. These were the test scores that we did in that class activity where we started looking at standardizing things. I look at my histogram up here, or my dot plot, which is close to a histogram. And I say to myself, okay, this looks roughly symmetrical. It's unimodal. Yeah, there's some weird variation, but for the most part, there's not a second peak anywhere. 65 does have 2 scores, but I'm not going to call that a peak. I've got that strong cluster in the middle. That's roughly symmetrical. So I'm going to go ahead and I'm going to look at my mean and my standard deviation. My mean and my standard deviation. So one standard deviation to the left should be 70, and one standard deviation to the right should be 90. 70 would fall at, again, remember we've got 20 test scores here, so 70 would fall at 4 out of 20, or there would be 3 scores behind it out of 20, so 70 would mean that you're in the 15th percentile. 90 would mean that there's only 3 test scores above it, so that means that it would be in the 85th percentile, because there's going to be 17 test scores lower than that 90. I quickly do my math here, 85 minus 15, and that gives me 70%. All right, so I've got 70% of my data within one standard deviation. This is proximal to 68%, so I could still be looking at something fairly normal here. I will do another standard deviation. My second standard deviation is going to be at 100, and my next standard deviation down is going to be at 60. And I can just look at this and I can see that 100% of my data falls between 2 standard deviations. And I can't even go out to a third standard deviation. So I've got 100% of my data falling in 2 standard deviations. Now I'm thinking that this is probably not super normal. This doesn't look like a normal distribution to me anymore. Sure, I've got 70% in one standard deviation, which is kind of proximal to 68%. I moved on, but I shouldn't have 100% of my data in 2 standard deviations if it's normal. I went through and used an internet graphing utility to figure out this normal probability plot. I plotted the test scores and what their percentile is versus what their expected percentile should be. So based on what their percentile is, I found what their expected z-score should be and then plotted the normal probability plot. And we can see here that this really isn't a straight line. If I did like a straight line between the points, that makes it look more straight than it is. We can see a lot of variation here, especially right here. We kind of see almost, in my opinion, like a cube root looking function exist. That's not a straight line. There's way too much variation, especially this like straight up and down part. So what we could say is, I'm not going to say that this is close to normal, but I could say that based on the fact that this line isn't straight and the variation here is really strong, that this probably isn't a normal plot. It's definitely closer to normal than a lot of data points are. I mean, you see in your reading how you have that one normal probability plot that looks downright logarithmic where it goes like this. And that's very clearly not normal. This one you can make an argument for it being close to normal, especially having 70% of your data within one standard deviation, having this roughly symmetrical chart, having a normal probability plot that isn't linear looking. It doesn't seem to be linear, but it also the variation between that linear, like between how linear it is, isn't strong, but it's not normal. It's kind of close to normal, but it's not. All right, you guys have a homework assignment. A few of these are going to be more difficult because you don't know what to do without a calculator yet, and you're going to get that calculator lesson in class the next time we meet. So just hold your horses, be patient. We'll go over that. It will all make more sense. Well, it's not going to make more sense, but it will be easier to find your values, easier to find your information once you have that calculator. So be patient there. Reach out if you have any questions or concerns, and have a great night.